Okay, so just before break we talked about Coulombs Law, and what I want to do today is solve a couple of simple problems using Coulombs Law, remind ourselves what we mean by an electric field, and then get ourselves ready to do some problems for homework. A couple of Coulombs Law problems probably on Tuesday, and then a couple of more complicated electric field problems where you have to use integration to find the electric field on Thursday. So if we remind ourselves, right before break, we were talking about Coulomb's law, which says that the force between two electrical charges is equal to the product of the electrical charge divided by the distance squared times some proportionality constant, which at the time we just called K, and the value of K is 8.99 times 10 to the ninth Newton meter squared per Coulomb squared. This actually isn't the version of Coulomb's law that we usually see in an advanced physics class. We usually see this version of Coulomb's law that's written in terms of this other constant called the permittivity of free space, or epsilon zero, or sometimes epsilon naught is the way a lot of physicists will say it. Zero being the sort of an old British not being sort of an old British term for the number zero. The only difference is the way we frame the constant. It turns out that some physics equations, namely Gauss's law, look simpler without the 4 pi in there and with the thing written in terms of epsilon naught instead of k. So we'll usually see Coulomb's law written that the force between two charges is equal to the product of the two charges divided by the distance squared times 1 over 4 pi epsilon 0. Last time we saw that we can also think about this in terms of an electric field. We can think about a charge Q in space, Q, as creating a influence, a disturbance, a something in space called the electric field, and that some other charge, let's say little q, that finds itself in that electric field will experience a force equal to its charge times the strength of the electric field at that point. So an electric field is a vector field in 3 dimensions, and the force on an object is equal to its charge times epsilon naught. So if we want to write the it's charge times E, the electric field. So if we want to write the electric field due to a point charge in space, that electric field is equal to 1 over 4 pi epsilon 0 times the magnitude of that charge divided by the distance squared. So the electric field of an object falls off inversely as the square of the distance, just like the gravitational field. And we talked about some of the geometrical reasons why so many 3-dimensional fields follow a 1 over r squared law. So let's just look at a couple of examples of how to solve these problems. The first example in chapter 21, example 21-1, asks this. Suppose you've got two charges a distance L apart, where L is 30 centimeters. What is the force that each charge exerts on the other? And obviously, because of Newton's third law, that force will be the same. The force that charge 1 exerts on charge 2 will be the same as the charge that 2 exerts on 1. The charges of the two objects are given in actually microcoulombs. A coulomb is quite a bit of charge, so often you'll see the charges of objects given in microcoulombs or even nanocoulombs sometimes. So let's go ahead and just do this simple calculation. Coulomb's law says the force on these two objects is going to be equal to 1 over 4 pi epsilon 0 times the charge of 1, 50 microcoulombs, times the charge of the other, 1 microcoulomb, divided by the distance between them, which is 0.3 meters, 30 centimeters. And we can't forget to square that for the inverse squared law. Where, again, this whole thing, 1 over 4 pi epsilon naught, is the thing that we were before calling k, 8.99 times 10 to the ninth. I'll just go ahead and move this up here. 8.99 times 10 to the ninth Newton meter squared per Coulomb squared. So that's all the information we need to go ahead and calculate that. If I bring up my calculator, let's see, we've got 50 microcoulombs, so that's 50 times 10 to the negative 6 coulombs times 1 microcoulomb, that's 1 times 10 to the negative 6, divided by 0.3 squared equals, and then times that constant, which is a big number, times 8.99 times 10 to the 9th Newton meter squared per Coulomb squared, gives us 4.9944, so we can just round that up to 5 what? 5 newtons force. So calculating the force between two electrical charges is no different at all than calculating the force between two objects using the law of gravitation. So I'm going to go ahead and pause the video, and then the next video we'll look at a little more complicated situation where the charges are not equal.